Yes. Hey everyone. Good evening. Am I audible? Please let me know in the chat box. Okay. Okay. Great. Yeah. So let us start this session. One second. Give me a second. Yeah. Before going to start this session, is it visible in live? One second. Yeah, we are all set to start the session. Yeah, before going to start the session, how many of you know about SPA protocol? If you know about SPA protocol, type yes, or if you don't know anything about SPA protocol, type no in the chat box so that I can come to know like how many people know about SPA protocol and how many people don't know about anything about SPA protocol. Can I please know in the chat box? Okay, from IoT perspective, okay. And others also try to please respond, okay. No. Okay. So, anyways, we are going to discuss about SPI protocol so that if any person who is watching this particular session will be able to get the insights about SPI protocol. Obviously, we need SPI protocol for this particular project, right? So, anyways, we are going to first of all discuss about SPI protocol. Then we are going to start with our project, right? Now, let me share my screen. Give me a second. So this is a part of our Verilog project development series where every week we try to, you know, do one project related to Verilog as of now. And in future, we are trying to implement with system Verilog project development series. Like we are going to develop test benches every week, like weekend, Saturday and Sunday. This is what I'm planning. And let's see. And in this week, we are basically trying to develop SPI based EEPROM development, right? Yes, it is live on YouTube and it will be recorded and I will be sharing the recording links also so that you can watch it again. Yes. So first of all, let us try to discuss about SPA protocol, where SPA stands for Serial Peripheral Interface, where it is going to use for connecting with my interfaces, right? Now, coming to SPI, as I've said you, it is a serial peripheral interface protocol where it's a synchronous protocol. And why it is synchronous? Because master is going to provide the clock to the slave, and both master and slave are going to work with the same shaded clock. Okay, and it's a full duplex. It's a serial communication protocol where serial communication, in the sense, you are going to send the data one by one bit. You are going to send for every particular edge of the clock. Okay, and it's a short distance communication between a microcontroller and one of the peripheral devices, and it is developed by Motorola, and it operates in master slave controller peripheral configuration, and it is going to use a separate clock line, unlike your UART protocol where we were not having a common clock line, where we were using for synchronization, we were using baud rate configuration. And it is commonly used for sensors or memory chips and displays and SD cards. That is what we are trying to implement it now. We are basically trying to have the interface with our memory chips. Okay. And in our previous Verilog project development series session, we were discussing about UART based LED control, right? If you want to look into it, you can also once go through that, right? Now, so coming to this history of SPA protocol, this is how the SPA protocol was evolved. You can once look into this PPT. I will be sharing this PPT. And the key features of SPA protocol is full duplex, and it's a synchronous protocol, and it is high speed compared to UART and I2C. And it's a simple protocol, and it can basically support multiple slaves. Give me one second. There is some disturbance over there. Yeah. So coming to this, it's a full duplex, synchronous and high speed, and it's a simple protocol where we are not going to have any kind of address or start or stop bit, or it's not a complex framing we are going to have. If you know about UART protocol, we were having some kind of start bit, data frame, and parity bit and stop bit. But in the case of your SPA protocol, you're not going to have any kind of frame. And I2C also, if you know about I2C protocol, in I2C also we were having some kind of start, addressing schemes and acknowledgement and data and again stop it and all. But in the case of SPA, you're not going to have any kind of framing and all. Okay, just if you want to send the data, send it. That's it. And it can basically support multiple slaves, and it can basically have flexible data size. It's not restricted to 8 bits. If you want, you can configure up to 32 bits. We are going to configure. Okay. Now, and coming to SPI, we are going to have basically four lines. One is serial clock, where this particular serial clock is going to be generated by the master and received by the slave. Master, when it is going to send the data, it is also going to send the clock. Okay. Now, before that, I hope you already know what do you mean by master and what do you mean by slave. So, a particular component or a device which is initiating a particular transaction, it is known as a master. And a component which is basically responding to that particular transactions is nothing but my slave. Okay. So whoever is a master, whoever is being configured as master, they are going to basically send the data via they are first of all going to send the clock, and next we are going to send the data. Okay. So all the data which we are going to send, that will be synchronized with my clock, and I'm going to have something known as MOSI. MOSI is nothing but master out slave in. That means whatever the data I'm going to send from master, that will be carried out using this line, which is nothing but MOSI. And this line is a serial interface, or it's a serial line. That means you're going to send only one bit per clock. And MISO is nothing but if you want to read the data, you're going to use something known as MISO. MISO in the sense master in slave out. Okay. And let's say suppose if you want to select the slave and if you want to, have the communication with this particular slave, you are going to use something known as slave select, and some configurations you might see this chip select. So using the slave select or chip select, you're going to select that particular slave. Okay. And this is active loop. That means if it is equal to 0, then your slave will be selected. And if it is equal to 1, your slave will be deselected. Okay. That is why it is known as active loop. Okay. So these are the pin configurations of my SPA device. And now coming to, if I'm going to have multiple slaves and a single master, I'm going to have for every particular slave a dedicated chip select line, so that let's say suppose if I want to communicate with slave 1, then I'm going to make this chip select 1 is equal to 0 and chip select 2 is equal to 1 and chip select 3 is equal to 1. At a time, I can basically able to communicate with only one particular slave. And let's say suppose if I want to communicate with slave 2, I'm going to give chip select 2 is equal to 0 and chip select 1 is equal to 1 and chip select 3 is equal to 1. So this is how I'm going to communicate if I'm going to have multiple slaves and a single master, right? So up to here, is it clear? Any queries or any doubts over here? So these are the basic, protocol insights and basic pin configurations and all. Is it clear? Are you following me? Any doubts or any queries over here? Okay, that's great. And if I have single master and a single slave, I'm going to have only four lines. One is S clock as we have discussed now, and one is MOSI, and another is MISO, and another is slave select. And it is basically ideal for simple designs like a microcontroller reading a single SPA temperature sensor or writing one to EEPROM. That is what we are doing in our project today. And if I'm going to have multiple slaves, I can have this chip select as I've said you already. And I can have one more configuration which is known as daisy chain configuration, where uh, your master is connected to one slave, and from one slave you're going to connect with another slave, and from slave 2 you're going to have the connection from slave 3. This is nothing but my daisy chain configuration, where I'm going to have only single shade chip select left. Once you can refer to this daisy chain configuration, just I'm giving you an idea. Like we have two kind of topologies, where if I'm going to have multiple slaves and we are only going to have one slave in our project, and we are going to deal with one master and one slave, that's it. Okay. And yeah, now how are we going to basically send the data and sample the data? Let us try to understand. Let's say, suppose this is my master and this is my slave. So this is my master and this is my slave. First of all, my master is going to generate the clock and it is going to give it to my slave. Okay. And if it is configured in write mode, then my master is going to send the data from master to slave. So master is going to send the data in the write case, where I'm going to use MOSI pin for writing the data. And if it is configured in read mode, then I'm going to read the data using this MISO pin. And before that, I need to select the slave. Then only I can basically have the communication with this particular slave. Okay. Now, let's say, suppose if I'm going to have this S clock, let's say this is my clock which I'm going to have. Whoever is going to send the data, that is, in the case of my write operation, it is my master. It is known as driving or shifting. So these terminologies are very important. Why I'm discussing this is because some people get confused over here if they are not aware of this basic terminologies. That's the reason I'm discussing them. And whoever is receiving the data, that particular operation is known as sampling. Okay. Now, let's say if I'm going to drive and sample at the same clock edge, D is nothing but driving and SAMP is nothing but sampling. If I'm going to drive and sample at the same clock edge, what is going to happen? Am I going to sample the data correctly? If I'm going to drive the data and as well as if I'm going to sample the data at a positive edge of the clock, am I going to sample the data correctly? Yes or no is the question. Anyone wants to answer? What do you think? If the driving and sampling is happening at the same clock edge, will my master is going to sample the data correctly? Yes or no? Obviously no, right? Okay. I cannot have the driving and sampling happening at the same clock edge, or I cannot have driving and sampling at the same edge of the clock. That's the reason what I'm going to do in this particular protocol. So what the protocol is specifying us is you do driving at one edge and you do sampling at another edge. Okay. If driving is happening at the positive edge, then you do sampling at the negative edge. Or if you are driving at the negative edge, you do sampling at the positive edge. This is how we are going to avoid the race condition. If driving and sampling is happening at the same particular edge, then we are going to get race condition. Race condition in the sense we are not going to properly sample the data. Okay, so that's the reason what are we going to do is we are going to basically drive at particular edge and we are going to sample at particular edge. Okay, now let's say if this is my clock, if I'm going to have this clock with me, we also need to decide what is the idle phase of this clock and what is the working phase of this clock. And if I'm configured as a master, I need to know what is the active level of the clock and what is the inactive level of the clock. So I have active low level and active high level. Okay. So this is low level of the clock and this is high level of the clock. Now I need to decide what is the active level of the clock, whether when your clock is active, whether at high level or whether at low level. This also I can configure in SPI protocol using one signal which is known as clock polarity. So using this particular signal clock polarity, if this signal is equal to 0, then that means my idle phase of clock is 0. So if S clock is equal to 0, then it is configured as idle. And if my clock polarity is equal to 1, then idle phase of clock is 1. So this is how I'm going to decide when is my clock idle, whether it is equal to 0 or whether if it is equal to 1. Then I'm going to decide or I'm going to configure using this clock polarity signal. Okay. And when to shift the data and when to sample the data is basically decided by your clock phase. There will be one more signal which is known as clock phase. So depending upon this particular signal clock phase, I'm going to decide when to sample the data and when to shift the data. Okay. So using this two signals, I'm going to decide when is the idle phase of the clock and when I'm going to shift the data. Let's just suppose if my clock polarity is equal to 0 and clock phase is equal to 0, then what I'm going to do is my idle phase of clock is 0. My clock will be idle when S clock is equal to 0, and shifting is done at immediate positive edge of the clock, at positive edge of the clock. That means over here. Okay. So sampling is done at this particular positive edge of the clock, and shifting is done at this particular positive edge of the clock, and sampling will be done at this negative edge of the clock. So this is how I'm going to configure, like when should sampling should be happening and when shifting should be happening. Okay. So this is what the table is basically telling us: when should we sample and when should we shift it. Okay. So, anyways, we are going to discuss this particular table, and in our particular project, we are going to shift the data at positive edge of the clock, and we are going to sample the data at negative edge of the clock. This is we are going to basically have mode zero configuration. This is known as mode zero configuration. This is what we are going to follow in our project. Okay. Yes. So, up to here, is it clear for everyone? Any doubts or any queries? Okay, great. So that was about the protocol basics, and you no need to worry about the frame structure and all, because when you are learning about UART, there are many things like what is a start condition and how you are going to frame a data and how you are going to receive the data, what is parity. You are going to calculate this, and if you are learning about I2C protocol, you need to know about start condition and when you are going to deal with SDA and how you are going to format your address and all. But in SPI protocol, you don't need to worry about anything. One thing you need to do is you need to first of all configure how many bits of data you need to send via the MOSI, or you need to configure how many bits of data you're going to receive from the MISO. That configuration should be done in prior only. During the runtime, you cannot say, no, no, I don't want 8 bits. I'm going to send 10 bits of data. No, once 8 bits of data is configured to be sent, then only 8 bits of data will be only sent. Okay. Now, how you're going to send the data, you're going to send using this MOSI. Okay. So on this particular MOSI, you're going to send serial data. And on your MISO, you're going to receive serial data. Okay. Now, this was about our SPI protocol. Any doubts or any queries over here? Shall we move forward? Okay, great. Now, if you're working with actual FPGAs, how you are going to work with this SPI controller and what is this EEPROM? Let us try to have the discussion. And let me share one more screen. One second. Yes. So before going to discuss about EEPROM, can anyone tell me what are the different kind of memories do we have? Anyone knows what are the different kind of memories do we have? I'm waiting for your responses. Volatile memory and non-volatile. Exactly. SRAM and DRAM also correct, but the general classification starts from the differences between the memories, volatile memory and non-volatile. Now, the next question, normally, if you might face in your interviews also, these are very basic questions like what is a volatile memory and what do you mean by non-volatile memory? What is the exact difference? Anyone wants to explain in a word? You can also unmute your mic if you want. You have an option. Volatile keeps data if the power is on. Okay. My question is, what is the difference between a volatile memory and non-volatile memory? Others also? Fast and slow? Okay. Non-volatile keeps the data even the power is off. Okay. Yes. So coming to volatile memory, when you are turning off the power, you are going to lose the data. Whereas in the case of non-volatile memory, whenever you are turning off the power, even though if you are turning off the power, you are not going to lose any particular data. Okay, that is the difference between your volatile memory and non-volatile. Any application where you can use non-volatile memory, you can think of using a non-volatile memory. Any application can you think of? Okay. Any application of any real-time application of where you can think of using a non-volatile memory. USB, SSD, hard disk, FIFO. Okay, I will give you one simple application of using a non-volatile memory. Like let's say suppose if I have a device, uh, like let's say suppose if I'm working with PCI protocol and if my device, whatever the device which I've developed, it is PCI compliant device, and if I'm going to insert it into the PCI slots, you are going to have something known as configuration data. Configuration data in the sense, it is going to store like vendor ID and whatever the base address, and it is going to store every particular details of that. Okay, and even if you remove the power source from it to that particular device, it should basically store all that particular information permanently. Okay. So in that particular case, you can think of using a non-volatile memory for storing your important configuration data. Okay. So this is where you can think of using a non-volatile memory. And volatile memory, you can think of having like a small caches and small RAM and all you can think of, right? Yes. Now coming to this EEPROM is a non-volatile memory and the data is going to persist with power is also removed. Okay, so even if you are going to remove your power, you're not going to lose any particular data. And this particular EEPROM is byte addressable. That means individual bytes can be erased and rewritten, unlike flash block arrays. So we don't know exactly, we haven't discussed about flash memory, so I'm not going to discuss this particular point as of now. And this particular EEPROM is written and erased electrically and in circuit, and no UV light kind of thing is not required in the case of EEPROM. If you have learned about the different kind of memory architectures, you might have seen about this kind of erasing memory using UV light and different kind of techniques. And in the case of EEPROM, you can basically erase the memory using the electrical signals, right? And it is slower and lower density compared to your flash memory, but it is more flexible for small configuration or calibration data. This is what I was talking about when I was taking an example of PCI compliant device, and it is going to have some kind of configuration data storage, right? Now, yeah, this is what I was discussing about. So you can basically store the constants or the serial numbers or the boot configuration or small lookup tables. You can basically store. I was taking some PCA example, right? Okay. Yeah. Now, so we have already discussed about the SPI bus, and so why SPI based EEPROM is the question. Now, why are we choosing this SPI based EEPROM? It is going to have lower count of signals where we are going to have only four signals. That is S clock, serial input, serial output, chip select. Okay, and if we are not using this particular SPI interface, then we should use 8 plus signals for EEPROM. Okay, let me show you the EEPROM chip for you. Where is this EEPROM? Okay, EEPROM chip signals. Okay, if we are not using SPI protocol, then obviously the number of signals we are going to use are going to take a lot. And it's a simple protocol. SPI protocol is not kind of addressing mechanism. It's not going to have any kind of frame structure it is going to have. It's a simple protocol. That's the reason we are using this particular SPI protocol, and it's low cost and it's widely supported. Now, coming to the memory interface which we are going to use is microchip 25LC256, which you can type it in Google and you can get the info about this particular memory interface, and you can get the data sheet of this memory interface, like how this memory interface and what are the internal configuration of this memory interface and how the array is being arranged in this particular interface. That is all we are not going to discuss. if you want to explore it, it's a very good topic to explore. Like you can explore like what exactly which is present inside this memory interface, and how and what kind of transistors are used. Like we are going to use something known as floating gate transistors. So those are all very good to understand. And if you want to really explore, you can explore it about the internal structure of this particular interface, right? Now, coming to this, it's a 256 kilobit SPI bus serial EEPROM, and this is what we are going to take in our project, where its total density is 256 kilobits, and it's basically having 32,768 cross 8 memory organization. And there is something known as page size that we are going to discuss. What do you mean by page size? Basically, it is of 64 bytes, and the maximum operating frequency is 10 megahertz. Okay, what do you mean by page size, and what is that we are going to discuss in great detail in our upcoming slides. Yeah, this is what I was talking about, the memory organization. If you have worked, if you have discussed, if you know about SRAM, and in our previous projects, we have done something known as SRAM controller. In our previous projects, we have done something known as SRAM controller, where we have discussed about what is the internal architecture of SRAM, what are the different kind of gates we are going to have and all. If you want to look into it, you can look into it. And the same kind of memory organization we are going to have in this also. And we are going to have something known as row decoder, column decoder, and we have discussed in great detail in our SRAM based controller in the Verilog project development series itself. Now, coming to the question, why not UART based EEPROM? See, if you want to work with UART based EEPROM, then the one of the factor is you need to have a frame. Okay, what is that frame I'm talking about? You need to have a start bit, you need to have a data, and you need to have baud rate configuration. Whatever the memory controller you are working with, there you need to have baud rate configuration, and whatever the sender you are going to have, that need to be configured with respective baud rate. Okay, and if you're working with UART, it is very less speed compared to SP and I2C. Okay, and it's asynchronous. That means there is a chance of losing the data, and it's not like you cannot risk with the data which you want to store it in your memory, and you cannot take a risk of losing the data which you want to store in the memory. UART can be used like for serial debugging purposes. In debugging, if you lose a single byte of data also, it's not a kind of problem. Okay, but if you are dealing with memory kind of thing, and if you want to store any critical configuration data, you cannot take risk with using UART. And one more thing is, you are fixed to a constant size. Like it is, UART is going to support from 5 to 8 bits only. But SPI protocol, you can go up to 32 bits and 64 bits. That is the reason we are not going to use UART, and we are going to prefer SPA. Okay. Is it clear, Tejish? Any other queries? Okay. Now, what is a page size? So let us try to understand what do I mean by this page size. Let's say suppose if I'm going to have a particular EEPROM present with me. This is my EEPROM which is present with me. Now what is that I'm going to do? I'm going to make this chip select is equal to 0, and I'm going to provide the clock S clock, and I'm going to provide the serial input to this particular memory. And let's say, suppose if I'm going to send 1 byte of data, okay, for every particular S clock, I'm basically trying to send 1 byte of data. It's not like I'm trying to store 1 byte of data and then it is going to, process it, and it is going to store in your internal arrays. So if you want to see the internal array architecture, let me show it to you so that it will be clear what I'm speaking about. PROM internal architecture. Yeah, you're going to have something like this. Let me show you for SRAM. It will be. So this is how you're going to have the internal array architecture, where this each particular cell is nothing but SRAM cell, and this is being implemented with a capacitor and a simple. I think it's a capacitor which is being implemented, and you're going to have something known as address decoder and row decoder and sense amplifiers and all. This is what we have discussed in our SRAM based memory controller. So whatever the data which was sent, that will be configured into each and every cells, right? And when you are sending the data to your EEPROM controller, I mean EEPROM chip, that this particular chip is also going to have some kind of internal memory architecture. And whatever the data you are going to send, that is not directly stored inside your byte. So it is basically going to have something known as page buffer, where it is going to store the data into that particular page buffer. And after the user has sent all the particular data, it is going to forward the data from the page buffer to this particular internal memory architecture. Okay, so let me explain what is that happening again. So whatever the data which I'm going to send, let's say suppose if I'm going to send 32 bytes of data, okay, then what is that it is going to happen after sending this particular 32 bytes of data internally in this memory chip, it is not going to push all the data into the memory cells. No, first of all, it is going to basically store it into the something known as page buffer. From this page buffer, after user has sent every byte of data, then from this page buffer, it is going to forward it into the memory architecture. This is what it is going to happen. So that is nothing but my internal page buffer. So EEPROM cells can't be programmed instantly. And instead of writing each incoming bytes straight to the array in the sense I've shown you, right? This part. So it is not going to push each particular byte of the data instantly into this particular array, but the device is going to first stage the bytes in a small internal page buffer. And then it is going to commit the whole page in a single internal programming operation. Okay, so that is nothing but my page buffer. It is going to basically hold the data temporarily until the user is going to send all the particular data. After user has completed sending all the bytes of data, then this page buffer is going to move that particular data into the memory. So buffer is this particular page buffer can hold up to 64 bytes. Okay, and bytes are not written into the array as they are going to arrive. You can see in this particular block diagram where from the SPI interface we are going to send the bytes of data, and we think that it is being stored in the memory array directly, but no. First of all, it will be stored inside something known as buffer, page buffer. So you can send up to 64 bytes of data. After sending, after completing this particular operation of sending the bytes, from this particular page buffer, this bytes of data will be pushed into this memory array. Okay, so that is what it is written over here. So buffer holds the data up to 64 bytes, and bytes are not written to the array, and nothing is programmed until chip select goes high. Okay, so until and unless chip select is made to high, that means end of the particular transaction. That means this memory will come to know that okay, user has provided all the data to be stored. Then after providing this chip select is equal to 1, then it is going to program the entire array at once from this particular page buffer. This is what the process is going to happen. Is it clear, guys? Anyone having any queries, or shall I repeat this particular part again? This is a very, very important part, and this is what we are going to look into our Verilog implementation also. This feature we are going to make sure and we are going to follow this feature. Is it clear? Any doubts or any queries over here? Okay, great. Now, so this is what it is going to happen. So master is going to send the data, and how it is going to send the data? It is going to make our chip select is equal to low. Okay. Whenever chip select is equal to low, then that means your slave has been selected and you want to perform a write operation. And we are going to have something known as write command. Okay. I will also show you some opcodes and commands which we are going to have. Let me show you this opcodes. Yeah, these are the different opcodes which I'm going to have. So see how the memory is going to come to know that user wants to perform a write operation, or user want to perform or disable the write operation, how or what the user wants to do. So for every particular operation, we have some set of commands. Okay. As we are going to refer to this particular command sheet, and whenever we are going to send the data or the address, we are going to send this particular opcode so that our memory will come to know that okay, user wants to perform this particular operation, or our chip will come to know that okay, user wants to perform this operation. Okay, we will discuss about this instruction set opcode and all. Now, so what is that we are going to do? We are first of all going to make sure that chip select is equal to low. Then we are going to provide the write command. and then we are going to provide the address of that particular chip, and it can be of 64 data bytes. And it is not programmed yet. If you are sending a particular byte of data, instantly it is not going to program at that particular instant, but it is being buffered into some internal page buffer. Okay. Now, after that, when we are going to make our chip select is equal to high, then EEPROM is going to read this particular page buffer, and it is going to fill all the internal cells, and it is going to program all the internal cells. Okay. So for this programming, it is going to take few time. That is what we are going to discuss in our next slides. Okay. So that is known as write in progress. So it is going to gate every subsequent access until the program is going to complete. So internally, the programming of this arrays is going to happen. So in meantime, we are going to have some signal which is known as write in progress, so that user will come to know that okay, internally the array is being getting programmed. So the user will wait until sending another byte of data. Okay. Is it clear how we are going to program? Yes, it's kind of storing and sending. Okay. Yes. So let's say suppose why buffer 64 bytes at one time. So let's say suppose without a buffer, if we are going to have 64 bytes of data, let's say suppose for 1 byte of data we are going to take 5 milliseconds, then for 64 bytes of data we are going to take total time of 320 milliseconds. Okay. Now let's say suppose if I'm going to have a buffer in middle, if I'm going to have internal buffer in middle, then for 64 bytes of data I'm going to transfer in one write. So you can see over here, so it means one full EEPROM programming operation. The SPI transfer itself took a few milliseconds, and the internal programming that follow takes 2 to 5 milliseconds. Okay. So I've told you, right, from internal page buffer to array, the internal program is going to take around 2 to 5 milliseconds. That means whenever you have sent 64 bytes of data, that will be stored inside your internal array, and whenever you have made your chip select is equal to 1, entire 64 bytes of data from the internal page buffer is going to flow into the architecture. That means array architecture within 5 milliseconds. That's it. But if you don't have any particular internal buffer, then for each byte of data, if you're going to take 5 milliseconds, for 64 bytes of data, you're going to take total 320 milliseconds to fill the entire array. But using a buffer, it's going to take only 5 milliseconds of time. That is the reason we are going to use a internal buffer, so that internal buffer is going to program all the arrays within 5 milliseconds. Is it clear, guys? Why are we using internal buffer? And we are not sure about how the buffer is going to program the array cells. It's all the technology that particular vendor is using. It's all proprietary. Okay. So we are not, if you want, you can once explore it, but I'm not sure about how the internal array cells are being programmed from the page buffer and all. It's completely again the internal architecture, and it's a interesting topic which you can, if you want, you can try to explore. But from the top level view, you are going to know that there is some kind of buffer in between. And if you are going to send any particular data, that will be stored inside your buffer. And from the buffer to the internal array cells, it is going to take 5 milliseconds of time. Okay. Yes. And this is the 8-pin package which I'm going to have, which is chip select, serial out, and write protection, VSS, VCC, hold, SCK, and SC. So first one is chip select. So it is basically active low chip select which I'm going to have, and if this chip select is equal to 0, then I can basically able to communicate with this particular memory. And next is serial output. So that means if I want to get any particular data from this memory, I'm going to use something known as SO. SO is kind of MOSI pin. MOSI is nothing but master or slave in. Okay. And next is write protect. That means if this active low hardware write protection pin, and when this WP is equal to 0 and status register WP is enabled. Okay, we will discuss about this. Without discussing about registers, I cannot go and discuss about this write protection and all. And VSS is nothing but it's a power pin, and serial input is kind of MOSI pin. That means if I want to write any data into this particular memory, I'm going to use a serial. And write protect we will discuss, because without discussing about the internal registers and all, I cannot discuss about this particular thing. And S clock is serial clock, and hold also Hold is kind of thing where if I want to hold the operation temporarily, or if I want to pause this particular SPA communication temporarily. And another is VCC. So these are the different kind of pins which my chip is going to have as the interface. Okay. Now, so these are the key electrical characteristics. I will share the slides with you once you can check it out, all the key electrical characteristics and all. And SPA clock modes, we are going to use mode 0 as of now. Okay. Yeah. Now, this is what we are going to implement in our project. So what are we going to implement is we are going to implement our this particular green shade. We are going to implement this SPI EEPROM top, where it is going to have EEPROM controller and command FSM and SPA master, which it is going to communicate with this particular physical chip. Okay. Now, we can have any user bus. We can have an AXI user bus. Let's say suppose if you are working with FPGA and if you want to communicate with this particular memory, but this memory is having SPI interface. So you can build this and you can wrap this SPI interface inside an EXI interface and you can communicate this particular block with your processor so that you can have the establish the communication. Okay. Now, so we are going to develop this EEPROM controller, command FSM and SPI master, and we are going to discuss what is the role of this and how to code this and all. We are going to discuss in great detail. And yeah, so up to here is any doubts or any queries? Okay. Now, we have different kind of op codes which we are going to follow for our memory to come to know what kind of operation we need to do. Okay. So the first very op code is write enable. Like it is going to basically enable the latch and it is going to enable the write operation. And the op code for it is hexadecimal 6. And if we want to disable the write operation, I'm going to use the op code. That means if I'm going to send this particular op code to my chip, then it is going to disable the write operation. And if I want to read something known as status register, okay, inside your memory chip, you are going to have something known as status register. Now, what is this status register? It's kind of a register which is going to tell you some particular key informations. Okay, what are those key informations? So this is my status register. Where is the status register which is present? It is present inside your memory chip. Now, what are the key different fields which I'm going to have is first field is nothing but WIP. That means write in progress. So what is write in progress? Can anyone tell me now? This we have discussed in just previously in the previous slides. What is write in progress? From paging to the internal architecture, if the operation is performing, that is nothing but my write in progress. Okay. So if write in progress is happening or not, how to know? So if I'm going to read the status register 0th bit, I will come to know that, okay, write in progress. And next is write enable latch. That means if write operation is enabled or not, I'm going to come to know using this particular write enable latch. And BP0 and BP1, that is block protection and write protection enable, that we are going to discuss in our next sessions. That as of now, it is not necessary for us. So, and if I want to, where is this? Yeah. If I want to write into this particular status register, I'm going to use this opcode. And if I want to read the data from the memory array, I'm going to use this opcode. And if I want to write into this particular data memory, I'm going to use this particular opcode. Okay. Now, how exactly we are going to provide these opcodes and how exactly we are going to configure the status registers and all, that is what we are going to discuss. And what do you mean by write protection and block protection and read sequence and write sequence, and how are we going to handle this page boundary and what is this page boundary and all. We are going to have the discussion in our next session, and we are going to start our discussion of code implementations also. Okay. And if possible, if time doesn't permits in tomorrow's session, then we might extend this particular workshop to the third day also on Monday, or if during the weekdays, let's say if I'm not able to take time for this particular thing, then we are going to have it on next week. So by then, we are going to cover everything which is related for coding. Okay. So I'm going to cover everything which is related to which is needed for developing the code by tomorrow's session. And let's say suppose if I'm not able to start with the code, then uh, coding will be started in next week. Okay, so that is a plan which I'm going to have. So I can assure you by Sunday we are going to complete the entire theory which is needed for coding. Okay. Yes. 4, 5, 6 are reversed. What do you mean by 4, 5, 6 are reversed? I didn't get it. Yes. So that's about this particular session. If you have any doubts or any other queries you wanted to discuss, you can stay and discuss with me, or else we can wrap up the session. Okay. Thank you for joining in. Thank you. Hope this workshop was helpful and you have gained some insights. Thank you.